You are familiar with the term vapor pressure, right? Consider mixing two liquids, say ethanol and water. Can you tell me what the total vapor pressure of this solution will be? In this video, we will discuss the vapor pressure of binary solutions. First of all, we will discuss the vapor pressure of binary solutions of liquids in liquid with component 1 and component 2. The components 1 and 2 are volatile and completely miscible in all proportions. It was in 1886, a French chemist, Raoult, gave a quantitative relationship between the mole fraction of a given component and the pressure exerted by it in a binary solution. This relationship was known as Raoult's law, which states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. If P1 and P2 are the partial pressure of components exerted by components 1 and 2 respectively, then by Raoult's law, P1 is directly proportional to x1, the mole fraction of component 1, or P1 is equal to P10 into x1, where P10 is the vapor pressure of pure component 1. Similarly, you may write the equation for component 2. Now, by applying Dalton's law of partial pressures, the total pressure of the solution is the sum of partial pressures of the component 1 and 2. That is, P total is equal to P1 plus P2, or P total is equal to x1 into P10 plus x2 into P20. For a binary solution, the sum of mole fractions x1 plus x2 is equal to 1. Then you may write P total is equal to 1 minus x2 into P10 plus x2 into P20. Substituting this, you may see that P total is a linear function of x2 as P10 and P20 is a constant. That is, P total can be related to the mole fraction of any one of the components. A graph of partial pressure versus the mole fractions for components 1 and 2 gives a linear plot as shown here. Here you can see when mole fraction of first component becomes 1, then the partial pressure of the first component is the vapor pressure of pure component 1. A similar relation can be observed with component 2 also. You may also note that the vapor pressure of component 2 is greater than that of component 1. This shows that the component 2 is more volatile than component 1. The solid line shows total vapor pressure is the sum of the partial pressures of components 1 and 2. When the vapor phase is in equilibrium with the solution phase, then the composition in vapor phase is determined from the partial pressures of the components 1 and 2. You may use the equation P1 is equal to Y1 P total and P2 is equal to Y2 P total. This is true only if components are completely volatile and miscible. In a solution of gas in a liquid, that is, if one of the components, say component 1, is highly volatile such that it exists as a gas. Here, the solubility is given by Henry's law. The partial pressure of the volatile component 1 is directly proportional to its mole fraction x1 in solution. Comparing with Raoult's law, the proportionality constant Kh in Henry's law can be equated to P10. Therefore, we may say Raoult's law as a special case of Henry's law. Next, we will discuss the vapor pressure of binary solutions of solids in liquids, that is, Raoult's law for non-volatile solutes. Consider salt in water. Here, the non-volatile solute, salt, will not contribute to the vapor pressure. Thus, when a non-volatile solute is added to a solvent to give a solution, the vapor pressure of the solution is solely from the solvent, meaning P total is equal to P1 or P total is equal to x1 into P10. In such cases, vapor pressure of solution would vary linearly from 0 to the vapor pressure of the pure solvent. To conclude, Raoult's law in its general form can be stated as for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. Now, try to answer this question. Consider a solution of sucrose in water. The observed vapor pressure of the solution is lower than the vapor pressure of the pure solvent at the same temperature. Just now, you have learned that non-volatile solute will not contribute to the total vapor pressure. Then, how will you account for the decreased vapor pressure of solution?
Manorama Horizon. Learning made simple.